Well, good morning, everybody. Welcome to Phoenix. Thanks for coming. I certainly appreciate it. I just wanted to give you a brief on what I'll talk about today. I'll spend a few minutes just doing my CEO report card, some of the stats that we track, and making sure we serve customer base, keep everybody satisfied, keep good product coming. And then I'm going to address a topic that's hot today, which is artificial intelligence and machine learning. I'm going to keep it at a business level, not a technology level, but you can't escape this stuff these days. I mean, I was watching the hockey game last night, and I think there were 3 commercials that mentioned AI just on the hockey game about different things companies were doing with it. And it's present, something that we're going to start seeing more often, and it's really important. I just finished a certification at MIT Sloan in this area, and so I've got some pretty up-to-date information about what's actually happening and what companies are doing with it. So I'm going to give you a high-level flyby as to what's happening and why it's important, okay, and where it came from, basically, just so that you can relate to it. Now, a lot of it obviously may not come into play for a few more years, depending on your individual situations at your companies, but it's at least good to know what it is and what's happening around it, so you have a frame of reference. It's a general term that's being thrown around in the market quite a bit these days. So what's really AI, what isn't, what are people calling AI, and it's really not. I'll go through some of that, okay? In terms of background, I've met a lot of you over the years. I'm from a trucking family, Bellini & Sons Trucking in Boston. I spent my summers unloading freight cars, drove for Budweiser, delivering beer all around the city. I was in the union. I know it's a bad word for some of you, but I was forced to join the Teamsters when I was doing that in college. But my Uncle John got me in there. And then after that, of course, as I was working my way through school, and finally when I started in business, I got very involved in the whole side of business, which is about computing, computer technology, figuring out computer-based solutions to business problems. And so the foundation that I'll give you on AI today relates to that journey, what I went through, what I've seen, and where things have gone today. Okay. So in terms of the CEO report card, we've been continuing with the health checks. I'm sure pretty much all of you would have participated at this point. We're getting good feedback. It's always great to have direct feedback from the customers, do these health checks as frequently as possible. We've been able to cover across about 99% of the install base. Some of them happen quarterly, some twice a year, some once a year, depending on the size of the company and their willingness to participate with us. But it's been going along very well. We've expanded the value that we try to generate during the health checks. So it's not just, did you like these 10 things and click A, B, or C. We also make an effort to take a look at how you're using our products. So what % of our products are you using? And if you were able to use 100%, would there be a value increase? So we do a value gap calculation to say, hey, you're only using 60% of the product. If you could use 80% of it, you've already paid for it. Here's the value gap that you think you could cover and therefore generate more value for your company. The other thing we're doing is what we call the value increment, which is we have release plans, and of course, just like every user conference, that's the balance of what you're here for. You're going to hear a lot about our products over the next day and a half from all our product managers. But we're releasing features and functions on a constant basis. And so over the next 6 months, of course, we have a frozen calendar because we have to have frozen requirements, and then we have planned requirements in that 6 to 18-month period. And so we plan on discussing what's the value increment that you can generate from the new features and functions that we plan on releasing as part of the product. And so we've incorporated that into the health check too. So we're trying to make it a really valuable experience where we can come in as your partner, as your trusted advisor, because the nice thing about our view is that it's a consolidated view of the whole market. Because we do the advisory board meetings, we do the regional product-based user conferences like we went through last year, it gave everybody a chance to tell us what they were seeing in the market, where they felt the competitive pressures were, and then we try to translate that into new features and functions so that you can do better in the market, generate more value, compete better. And so that partnership, that ecosystem we've developed, a lot of it does run through these health checks in addition to the advisory board meetings and the different product-based user group meetings that we're running. So thanks a lot for the participation. It certainly helps. On the support metrics, 95% CSAT, and we continue to measure that as we go through the health checks. The R&D spend, over the course of the last year, since I've spoken to most of you, we had new investment come into the company. Symphony Technology Group came in. I've worked with them in the past. When I was running the IRI Analytics Group, Symphony was the investor at that time, so we're very familiar with each other, comfortable with each other. They saw a big future in what we could do with AFS, taking it forward. So they stepped in as the investor. Bill Chisholm, who's the chairman of our company, who runs STG, will be here this afternoon. So if any of you would like to have a few words with him, he'll be here for a few hours. Just let your, whoever is chaperoning you from AFS, let them know, and we'll track Bill down so you can introduce yourself and have a quick conversation. So, but they're very committed to our future, and it's going to be a great relationship going forward. And so they support not only the R&D spend, but the acquisition of complementary solutions. As a lot of you saw the press release recently, we acquired Exedra, perfect fit for us where we're headed in our TPM business unit. And Richard's here. Richard, can you stand up so people know what you look like? If you'd like to talk to Richard about Exedra and what it means to the business and how things look going forward, he'll be here. So please feel free to track him down and discuss that with him. On the collaboration, I mentioned that earlier. We tend to bucket our development. If you look at the R&D spend and the fact that we're increasing it, the way I like to do it is I like to spend 50% of the R&D on competitive advantage, competitive differentiation. So that's that first one, the competitive advantage piece. So that's 50% of our dev spend. The other 50% goes to technology, right? Because you have some technical debt related to movement, because it's not just all our software. We work with Microsoft and other partners, and their technology is moving all the time too. So you always need to make sure you're on top of your game there as technology shifts, not just what we write, but what we run on. So there's a lot of tech debt, so we keep an eye on that. There's maintenance, of course, so we invest in just the pure maintenance of the system. And then catch-up, and what that is we know that our competitors are always out trying to attack us on the market, saying they have something better than we do. So just let us know, and we'll put it into our release plan, and we'll come out with it in one of our future releases. So that's our catch-up bucket. So yeah, give us all the intel, because we're a partnership here. It's an ecosystem. So we started the alternating national and regional product-based meetings last year. Feedback was very positive. We felt, and we all have tight budgets, and I figured, well, it's good to have a national conference, but let's have it every other year. That way people can budget just every other year for this kind of event. And the regional ones, there'll be no fee. And we'll try to do them as close to the epicenter of most of the customers as we can. I mean, we're pretty spread out, but we try to get it as close as we can. Or a place where, if a lot of the customers live in the cold, we can put it in a nice warm place maybe, depending on the time of year. So, but those worked well, so we're going to do that as well. So next year we'll go back to the regional format where there's no fee, and then the year after that we'll again have a national conference. The automated testing, that continues to play a big role for us. The more efficient we can get there, the more investment we can put into the actual development of the product, not in the testing of the product. So that's, of course, it is a one-time expense when you buy those tools, but it's worth it for us. So we continue to make investments there. The other area we've gotten a lot into, not just the agile development, because we've been doing that for a while, but DevOps has come into play a big role in terms of how you actually develop within the agile methodology, the agile development methodology. And for those of you in supply chain, it's similar to what we went through there in terms of lean production, lean manufacturing. A lot of those concepts now have lend themselves into software development, agile development. So it's basically an application of that kind of theory in there. And of course, we continue to make platform improvements. Those of you in supply chain would have seen that with the movement toward the Ignition platform. We continue to make great upgrades in TPM, RE, the G2 product line. So a lot of investments there on the platforms. On security, we finished SOC 1. SOC 2 is almost complete. We just have a couple more products to run through, and then we'll be done there. For those that operate in Europe, GDPR, we're compliant with GDPR as well. So on that security front, we've got good accounting. Some of the customers have to run through audit on that. We participate in those, and everything runs fine there. And then documentation and training. You know, it's hard to keep up with all that all the time, but we're trying our best. We're putting investment there. I added some more people, online documentation, keeping it up with the releases and so forth. So I think you've seen the effect of some of the efficiencies we picked up on the implementations. Our implementation times have started to get shorter. We've gotten really crisp on those processes, how we work together, when we need deliveries from our customers, when we do our thing, and actually the go-lives have been going very smooth this year. So part of that's related to improved documentation and training that we're able to provide. Okay? So that's the report card. What I wanted to do with the first slide was just relate back to what I spoke about last year at the regional conferences and then the national, is this part of it hasn't changed. I mean, when you look at the data you have, what you'd like to do is you'd like to have executive dashboards, you'd like to have tactical dashboards where you've got visibility to your business. Hey, what's going on? You know, what did I plan to do and what are we actually doing? So I can see where there's any variances so I have a chance to make changes before, you know, the result is something I don't want. On the data side, you've got descriptive, predictive, and prescriptive. Now, that part on the data, even as I go into machine learning and artificial intelligence, really hasn't changed. The nature of it has changed a little bit. Descriptive is data you have. And so we have a wealth of data. We run analytics against it. We run reporting against it. We make decisions about it. So the data itself is stored in a way that makes it useful. However, the way it's stored is going to change a little bit under machine learning because most data and data systems have been designed for storage and retrieval, reporting, views, dashboards, and so forth. In artificial intelligence and machine learning, you actually have to interpret the data. So it's a little bit different. And a lot of the schema that have been set up to store the data hasn't been stored for interpretation purposes. It's really just been stored for storage and retrieval. So the data side of it does need to shift and adjust a little bit, and I'll talk about a few examples as we go through that. Now, the big problem area we have today is on the predictive piece. Predictive means you're going to create data that doesn't exist, right? The descriptive data is one thing. That's our data. We can look at trends, and we can look at what happened, same as last year, Sally method, and okay, what do we want to do this year? And that's real data. Predictive means you're creating data that never existed before. So the question is, can you trust it? How did you create it? And what happens is we have all these algorithms, whether you're doing optimization, linear programming, you know, whether you're doing some kind of stochastic forecasting, you've picked some algorithm that says, okay, I trust this algorithm. So I'm going to throw some data in it. It's going to create some new data that never existed before, and then I'm going to trust that new data and I'm going to run my business based on it. I'm going to make decisions based on this new data I just created. Well, who knows how good that data is you just created? What happens when you develop those algorithms, you do run test cases. But the problem is when you're running the test case, it's on a finite set of data. So as long as you model the constraint correctly out of that particular data set, then when you run that data through your algorithm, it's going to say, oh yeah, high prediction, 98, 99%, perfect. But then the problem is 6 months later, it's a slightly different data set. Maybe there's a different constraint in your business. And now the algorithm's still going to push out a number. You're still going to use it, but it's not going to be very accurate. So that's why you run post-event analysis to say, geez, what did we plan to do? What really happened? What did we miss? The algorithms are just a guess. Now, it's all we had to work with for a lot of years. I mean, we had to do the best we could. We made the best guesses we could in putting together those algorithms. But now machine learning is going to change all that. Because how do we learn as humans? We tell each other stories, right? I mean, we learn from stories. Hey, you know, when I did A, B happened. When I did X, Y happened. Wow, and this and that. Data is the story about what happened. If there's a way to take the story and go back and learn from it and say, hey, based on what happened last time, I'm going to do something a little different this time. So what it is the data itself is what's going to create the algorithm rather than us having to play around with differential equations and stochastic and this, that, and the other thing and just try to guess at it. We can actually use the resulting data, the story, and say, hey, that story was pretty good. I need to learn from that and go ahead and let that create the function that's going to give me the prediction. And that's why machine learning predictions are so much better right now, even in its limited application and rollout, than anything we've been able to do before. If you're working with software companies that say they do optimization or any type of regression or any type of stochastic forecasting or anything else. That's fine for now because that's all we had to work with. But believe me, in a few years, you are not going to want to be there. You're going to want to get on to what's happening with AI and machine learning. And so I'll go through that and explain how that works. So on the prescriptive piece, the prescription, remember on the descriptive data is fine because that's data you own, you have, you experienced it, and now you can make some decisions. On the predictive piece, things will change. And so as we get more into machine learning, we're going to get better predictions, and that means the actions we take related to that, the prescription, is going to get better and better for our business, and the results are going to improve. So just to give you a perspective on this, when I was running IRI's analytic groups, I did a lot of differential equations. Market mix was all this, market structure. I mean, everything that a lot of you in your companies, at different parts of your companies, have experienced about how you view the market, how you analyze the market, how you position product, how you create promotional lift, was created on these kinds of algorithms. And as you can see here, I never had a complete view of what I was doing. So on the build and decay functions, I had the decay function only. That was the only thing I could really model on the ad stock. On diminishing returns, a lot of people talk about diminishing returns and what's really happening there. All I could use there really was a natural log function. I couldn't really get the full picture, and so I was only able to model it partially. That's why you had errors in all these. And depending on the data set, sometimes the error would be big, sometimes it would be small. Same thing on time varying coefficients. Almost all the parameters were time constant. And I was trying to use constant to model varying because there was just no other way to do it. And so strategic aggregation, omitted variable functions, I mean, you know how hard it is when you get an incomplete data set and you say, geez, what am I going to fill the gaps in with? Well, let me take what happened before with the trends and seasonality and so forth. You might be missing the most important data. And now you're going to fill it in with some moving average of something that happened before. It's not the right view on the data. So that's why the results were sometimes good, sometimes bad. Because this is what we had to work with. We did the best we could. And I'm sure a lot of you are still using these. You might be using trade promotion optimization routines. You might be using market mix, market structure routines. You might be using certain statistical forecasting routines. That's what we had. And that's what you needed to work with. So that's what's available here. But what I'm telling you here is that it's not perfect, right? Sometimes good, sometimes not so good. And that's why your post-event analysis would have variance and gaps to what you had planned on doing. There's a lot of factors involved, obviously. But this is part of it. The analytics enabled through data. So machine learning is a form of AI that enables a system to learn from data rather than through explicit programming. So that's what mathematicians call that stuff I was talking about, is explicit programming. That's when you try to create all those algorithms and coefficients and all that kind of stuff. It's also called continuous mathematics because it's differentials, but that's the field. With machine learning, it's just so much simpler, and you'll see how we model it. It took a while for the computers and the software to get there, but it's a much simpler way to do it. Over time, as the algorithms receive additional training data, I get it now, you can produce more precise models based on that data. So that's the other thing. When I had the differential equations, they were what they were. I made my best guesses, and that's what we used. The thing with machine learning is the stories continue every day, every week, every month, every quarter, more stories, more stories, more stories. As the stories evolve to say, hey, I did A, B happened, I did C, D happened, the learning from those stories actually go back and change the algorithm to say, now I'm smarter. I just had something, I just learned something. And it learns and it learns and it learns, and they get better over time. Whereas with what we're doing today, you can't do that. So after the training, so you have to train the algorithm, just like you train a person, and use the data to do that. I'll show you how that works. When you provide the model an input, it'll generate an output. That's that predictive piece. So the predictive piece now all of a sudden gets better, and it gets better and better and better as you go. That's why I mentioned earlier, regardless of what you're using today, and you can keep using it for a few more years, you really need to start thinking about this because you're going to fall behind. And based on all the commercials you're seeing on TV, people are using it. I mean, it's getting out there, and it's getting out there fast. It's almost like Moore's Law. All that speed and advantage we took on the hardware side, we're now seeing it in what's happening with machine learning. It's just incredible over the last 5 or 10 years, the predictive accuracy of the models are just increasing so much. It's really amazing. And so you'll give it the input. So the predictive algorithm will create a predictive model. So when you provide the model with data, you'll receive a prediction based on the model you train. So very, very straightforward. Now, the one thing I will mention on machine learning that's a little uncomfortable for some. It's like, for my coffee here, let's say I wanted to take a drink. So I'm going to say, thirsty. I'll pick it up. I won't drop it. Take a sip. So people say, well, what did you do? And I said, well, I moved my arm. I thought I was thirsty. I picked it up, want to take a drink. That's at the top level. They say, no, what'd you really do? Well, my eyes my pupils are dilated up there. When I look down, the pupils, changed a little bit. And I gave a neuron motor response in my brain to move my arm. And I didn't crush the cup as I was picking it up. And it told me I could, hold it and then I had to move it. And then I used like my GPS head system to put it up to my lips. So that's not how you describe it, right? So what's going to happen in machine learning is you're not going to be able to say exactly how it came up with the prediction because it's learning through these neural nets, just like your brain operates. These neural nets in the computers are actually the ones that are learning and capturing the data and giving you the predictive results. What you're going to need to get comfortable with is that the predictions are superior. So if I'm comparing a prediction that's coming from the machine learning algorithm to a prediction I'm getting from some of these old differential equations, it's going to be better. And it's going to continue to get better and better and better. But if you're trying to go in and say, well, how exactly did it come up with the prediction? It's going to be the same thing as asking you, well, how did your brain neurons work when you took a sip of coffee? It's on that kind of level. So there's a lot of interest in that side of it as well, trying to figure out, well, how does it really make those decisions? And if you look at the self-driving vehicles, this has become a big ethical issue on AI as well. Because depending on how you program the vehicle, if something jumps out in front of your car, what should it be programmed to do? Should it smash you into the brick wall and take a quick right not to hit it, or is it okay to run it over so you don't get hurt? Well, that's going to be programmed into the vehicle. Well, who makes that ethical decision? Well, maybe it's different. If it's a child, you smash into the brick wall. If it's a dog, you run it over. I mean, who's going to make the decisions, right? I mean, there's a lot of ethical issues related to how the programs are going to be set. And so there's committees and people thinking about this stuff now. So, a brief history. I brought a few props here. So I mentioned AI. It's being used a lot in the market as a general term. A lot of people are throwing stuff. At MIT, they called it a suitcase term. But I said, I'm going to upgrade that. I'm going to call it a duffel bag term. Be a little more modern. So what's in this kind of general AI? And I said, well, the best way I can describe it is to tell you what I did. Because that way it's one-on-one. It's me personally telling you what I've seen, what I've experienced, and where this came from, so that you can ask me questions on it if you're interested in it. The first time I used artificial intelligence was back in the mid-'80s when I was working for the Department of Defense. I used it designing our nuclear submarines. So I could look at vibration patterns so that the radar of the enemies couldn't pick up our subs. And so I was using it for pattern recognition, and that's what ADA is. It was named after, I think, the daughter of the person who designed it, the software. The DoD paid for it. And so that was basically the very first instances. We used it on the inertial guidance systems for the nuclear missiles also. And so it was extremely important to understand vibration and patterns. And that was the very early usage of what was considered the first usage of artificial intelligence. Later, when I was over at General Motors, we created a program called Charlie. And Charlie's rule-based. Charlie was our best maintenance engineer at all General Motors. We used to do plant shutdown for 2 weeks every year around Christmas, and we had to go run around and fix all the robots and all the automation and all that crap. And Charlie was going to retire. It was like everyone was in panic. How are we going to be able to do this? So we had to interview Charlie for a few months and create a rule-based system, knowledge process system. That's also considered AI today, too. As a matter of fact, one of our larger customers recently had one of the big 4 consulting firms come in to tell them they were going to bring them into the new age with artificial intelligence. And you looked under the covers at what they presented. It was just a rule-based system. But you can call it AI. I mean, it's in that general AI bucket. Now, what we would probably do with that kind of system today is program a skill in Alexa. And then people can just interact with the skill through natural language programming. So this goes into the general AI bag. So pattern recognition and my rule-based stuff, this is my general AI bag over here. My narrow AI bag that we'll get to with some of our real examples is over here. So the next thing, community intelligence is huge. If you look at how the computer beat the Jeopardy champion, that was through community intelligence. It came from the internet. And this is the best-selling book, Where Wizards Stay Up Late. It talks about the ARPA program, where DARPA paid for the ARPANET. Now, it just so happens the project director is Frank Hart, my father-in-law. And so he's in the Internet Hall of Fame. I had a lot of exposure to this because I was working at Lincoln Labs at the time on the nuclear missile systems. And so it was very interesting, but it's this environment, it was the Internet environment. Without the Internet, none of what we're seeing obviously would have happened, but it's really this notion of community intelligence. And the way the computer beat the Jeopardy champion was the ability to go do like a Google search and correlate community intelligence in a way that enabled them to answer those questions. So community intelligence is also AI, and that's a big thing that goes in there. So that goes into our general duffel bag. The hardware had to get better. We needed more power on the hardware. This is a very interesting book. It's written by Murray Gell-Mann. He's a Nobel-winning physicist. And Murray was my advisor when I was running the internet company at MIT. And so I got to spend a lot of time with Murray. Murray actually worked with Einstein at Los Alamos. And he is the one that discovered the quark in nuclear physics and subatomic particles. And so that's where our quantum computing came from. And so I asked him, over many dinners, and I saw him lecture a couple of times, well, how did you figure it out? And he said, I had to simplify the problem. He said, what I did was I studied the way jaguars hunted and how they circled their prey and how those natural patterns occurred. And I was able to apply that thinking to the movement of subatomic particles. And then I had to simplify the charges. And he said, ones, zeros, and ones. He said, all my colleagues, and Einstein at the time was trying to prove his universal theory. Relativity, as we all know, was proven and is an important thing. Einstein tried to carry that and say, there's also a universal constant that proves there was no Big Bang. And he spent all his time on that with all these other coefficients. And Murray's had enough exposure to it, he said he felt that he was going he had taken it in the wrong direction. He said, I'm going to go in a different direction, and I'm going to simplify. And so with his combination of studying natural movements of predators and prey, along with simplifying the charges on the subatomic particles, he was able to discover the quark. And things went from there. So that's where the power of all our hardware came from. Simple. Zeros and ones, zeros and ones. Okay? The next one here, it's really important. Eli Goldratt, and some of you may have heard of his theory of constraints, a book called The Goal and so forth. He's another physicist, like Murray, that came into manufacturing. This is where optimization came from. This is one of the books, my quotes on the back here. I lectured a lot with Eli. And backpropagation is an important concept in artificial intelligence. And this is where the backpropagation first occurred, along with the optimization around the linear programs. And so he wrote his PhD thesis on this for physics, and then we applied it in manufacturing, first with finite forward scheduling, and then with supply chain optimization. So this was a seminal work in starting to figure out, well, what are the algorithms and what do they need to do? Because the backpropagation, as you will see in machine learning, is an important concept in how the algorithms are going to learn. So initially we did linear programming. So as I said, those of you using TPO systems, stuff like that, it's okay for now. But over time, you can't keep using them because the machine learning-based algorithms are going to beat them out. And so they're already beating them out now. So some of the concepts still apply, like the backpropagation. But what is not going to apply is the linear optimization that you're seeing in there. Okay. The next one, this one, Moore's Law, oh yeah. So I was going to have a little prop to show you, but it broke. I ordered a 300 millimeter wafer disk. I used to be the president of Brooks Automation. I went over to the hardware side for a little while, working with Intel on trying to figure out how to follow Moore's Law. What happened was, at a certain point in time when we were developing semiconductors, we couldn't get them any smaller because we had hit the wavelength of light. And a lot of the equipment we designed and the controls were based on being able to see stuff. And once we started to drop the size below the wavelength of light, we didn't have anything that worked. And so we had to figure out, well, how are we going to create new software, new machine controls so we can still automate the production of the wafers to continue building semiconductors as we continue to follow Moore's law. So the wafer I was going to show you, it looks like a record, and it's nice and shiny, and that's what comes out. And when you cut those big ingots into slices and you build the semiconductors on there, and then you have to cut them up. And you don't really know which ones you're going to get, because some of them are really fast, some of them are really slow. So after you cut them all up, then you got to test them all and see, okay, these are A's, these are B's, these are C's. So still not an exact science, but we made a lot of improvements there. But that's really where the power has come from now. And it's changed a lot of things. You hear a lot about big data, but big data doesn't matter if you don't have the processing power. And so it was the movement there on the hardware and being able to get sub-wavelength of light in the manufacture of your semiconductors that really allowed this to happen. The real-time enterprise, there was a certain point when I was at Brooks that I figured we had it all figured out. And so I wrote a book called The Real-Time Enterprise. And I said, well, now we have CRM. And when I was at Oracle, I was working with Tom Siebel. He had left Oracle. Larry didn't want to start CRM, so he went out and started his own company. And Mark Berenshay wanted to do Salesforce automation, and Larry didn't want to do it, so he went out and created his own company, Salesforce. And then supply chain management, I talked about that. We built a company around that. Larry didn't want to do that either. So we left and went with Ellie Goldratt and a few others and created a company called I2, which was supply chain optimization at the time. Theory of constraints came in. I talked about BAPROP. Genetic algorithms, I went back to MIT and bought a company that was at the forefront of genetic algorithms. And some of the problems there, those of you that work in scheduling, the first problem sets I applied it to was at the large trucking companies like Navistar, because the option combinations are just maddening, but that line rate needs to stay the same. So you have to be able to sequence the trucks coming down the line in a certain way based on the option content in order to actually keep the line going so you can produce the target number of trucks every day. You had to use genetic algorithms for that. Why is that important? Well, it's already playing in the machine learning AI market, Stitch Fix. Those of you see them, they're advertising all over the place now. They use a machine learning algorithm combined with a genetic algorithm. That's how they're doing what they're doing, and that's why they're gaining so much market share right now. They also have a human involved in the process. And as you'll find with most machine learning, is there has to be a human somehow in the process somewhere supervising what these outputs look like. Because if they didn't, the genetic algorithm would put out some really wacky stuff that people probably wouldn't want to wear. So it also puts out good stuff. So you need to have that together. Linear programming, object databases was another big thing. Back then, the databases weren't fast enough. The phone companies had gotten to a point where they could no longer run the hierarchical databases they had from the IBMs of the world. And so the only way you could actually get enough speed in the databases to do the switching on all the phone networks around the world was to go to an object database. So that was a huge advancement in terms of what happened there. So all those things together, I figured, okay, we can do real-time enterprise, but the problem was it was too general. It wasn't personalized enough. So the next thing, I went over and I spent some time in the healthcare industry because they were starting to use some technology and really start to personalize it. So Bill Frist was on my board of directors, so was George Shultz, the old Secretary of the US. And Bill in particular had gotten into the technology side of things, especially with what we saw with Moore's law, the power that was now available. And he's the one that started doing the DNA mapping so that you could get personalized medicine based on your own personal DNA. And the rule-based stuff, like Charlie we talked about before, that's prevalent in a lot of medical systems right now. They're able to personalize to say, based on what your DNA says, and based on what the predictions are based on your DNA, here's the regimen or course of treatment that we recommend. So this really starts to get at the one-to-one marketing we're seeing, because what's the big thing in CPG right now? In retail, food distribution, food manufacturing, everyone's saying, oh, everything's got to get one-to-one. We have to know what the individual wants. If we can figure out what the individual wants, then we know what the group wants, then we gain market share, revenue margin per square foot, and so forth. So it was really the medical industry that made the first big moves into harnessing all this power, personalization, the DNA mapping, and all that stuff. And now we're seeing it start to bleed back into our industry in terms of what we're able to do. And then, of course, you've got the big data piece. Michael Scott actually wrote a chapter in this book. He's the one that runs G2 for us. He's here today. And so the big data side is important, but you got to remember this could be a red herring too. The thing about machine learning, and the general AI stuff's all interesting, but like I said, if people are out shopping and people are pitching you on AI, it could be any of these things because they all actually fall into the AI duffel bag. What you want is machine learning, and I'm going to give a little more detail there. So it's general AI, which is all the stuff I just went through, versus narrow AI. And what you got to be careful of is companies trying to sell you that you need a big data repository, a data lake, data refinery. I mean, it's not about having one set of data across the entire company. It's about what pockets, what wells of data do you have that can provide real insights to your business. So you can use that well of data to make a better prediction so you can make a better decision about that part of your business. That's what's important. And so what you'll see in machine learning is you take those wells of data and you use them to help you learn more about your business, fine-tune your predictions, and make better decisions. Now, over time, you may end up with a big data lake and so forth, but that's really just the tool. That's not the target. That's not the objective. Okay? So that's our general AI bag. So machine learning versus general AI. General AI is a suitcase term. That's what they called it. That includes rule-based, if-then-else, the knowledge information systems like Charlie, search, linear programming, optimization, genetic algorithms, moving averages, regression, whatever. So that's our general AI. Machine learning actually groups in 3 areas. There's supervised. So basically, you give it a data set, and then you label it. That's a cat, that's a dog, that kind of thing, so it can learn if it's a vision system. Unsupervised, you're going to hear a term thrown around called deep learning. It's a subset of machine learning. What deep learning is it actually tries to mimic the way the neural patterns in your brain works. And so it can actually, like if you gave it a set of pictures and you didn't label anything, it would eventually figure out the difference between a cat, a striped cat, a spotted cat, a tiger, a lion. It wouldn't know what they are, but it would know they were unique. And then eventually when it's done, you can go in and then label it and tell them what they are. That method of unsupervised actually develops much deeper neural patterns and is a better and faster way to recognize whatever you're trying to do in machine learning. But it takes a lot more data to do it. Whereas unsupervised, you can use smaller data sets and teach it. So for most of you, if you just have a year of history in your ERP system, you can develop a machine learning algorithm. If you have a couple of years, it's even better. Okay? But as you go forward, once you've established it off the first year, and you then put more forward data in it, it just gets better and better over time. Reinforcement, it's a little bit different. That would be like the self-driving vehicle. If you run something over, it says, oh, that was bad. I don't want to do that again. So then it puts that in, or it hit a lamppost or something. Oh, that wasn't good. And so that's what reinforcement is. So a little bit different there. So the fear factor. So everyone's afraid, right? What's going to happen? Is this Skynet? And what's going to happen to us humans as all this stuff happens? So let's compare the computer to the brain. So the computer's electronic, we're electrochemical. The computer has billions of transistors, but we have billions of neurons. The computer operates in a nanosecond, takes us a millisecond. Computers really are mostly sequential. I mean, you hear about parallel computing, but if I have the disk, everything on there is just zeros and ones. It's and or. That's how semiconductors work. Well, yeah, this one, that one, it's basically zeros and ones. So they're really sequential when you get down to the hardware, whereas we're mostly parallel. And they had at MIT, they had one of those image recognition programs up. They said, throw a few pictures in, see what it does. So anyone here from Boston? Yeah, I'm a Patriots fan, so I had a picture of Tom Brady on there in the football field, so I put that in. And so it recognized. It said, yeah, this is an NFL player, he's on a field, and blah, 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 and all that stuff is perfect. So then I had another picture that was, I figured it was going to be a challenge. One of my friends had given me some bratwurst, some elk brats, and I cooked it up in some microbrew, the Four Peaks, and I sent him a picture of it. It was the cast iron skillet on the stove with the brats in it and the beer next to it. So I put that in, and it said I was at a laundromat because, because it saw the white appliance, right, and the skillet. It says, oh, yeah, it's at a laundromat. So, so it's hard. I mean, it depends on the neural nets and the images and, what it's going to be able to interpret. Now, a person, of course, so that's why like a child, 3 or 4-year-old child that's learning about their environment and they see and interpret, infinitely more powerful than anything a computer could ever do, right? So we're decades away from a computer ever being able to do what we can do on the right-hand side here. So what AI is all about really is solving very narrow problems. We have data wells that represent certain parts of our business, and we can use machine learning to solve very narrow problems. They are what they eat. That's it. So whatever you want the machine learning algorithm to do is dependent on the data you're able to feed it. How many features are in the data, and then it can understand the data, and then it's going to give you an answer, and that's what it does. So we are what we eat. That's basically all it is. So it's nothing to be afraid about. So let me give you a few of the examples everyone's probably heard about. So we saw Big Blue beat the World Chess Masters. This was an example of sequential. So basically what it did was the computer was powerful enough, and again, this is Moore's law, that based on the pattern on the board as it existed, it could calculate every possible move and then assign probabilities to it. And that's how it made its next move. Very straightforward. The next one, though, was more challenging, the game of Go. And some of you may have heard this example. There's a lot more potential moves in the game of Go, more of an Asian game. The Chinese masters are the world champions, and it took a few years to program the computer to beat the world champions, but it eventually happened. This is what led to really the more use of deep learning and neural nets, because what we had to do was model patterns. So you couldn't model next move. There were too many permutations. So what you did was you could model patterns and say, given this pattern, there's another series of patterns that I can employ that would give me a better chance of winning. Now, the way they trained the system was they had it play itself like 1,000,000 times. So this really isn't applicable to the real world, this kind of machine learning and AI, because we don't have millions of examples we can give them when we're running our business every day, every week, every month. So it worked here, and it's a good proof of the theory, but it's not something that you can really, for games it's fine. But for what we're trying to do, it doesn't apply that directly. But it was good to begin to understand, if you look at what IBM Watson's doing right now, this is where they are. They call them knowledge graphs. And so they're trying to imprint various levels of deep learning and neural nets, and they're calling them knowledge graphs. So that's where all that stuff went that you heard about years ago. So what's real to us then, well, how does the Netflix recommender work? So we're Netflix, you might like this movie, you might like that, you're not going to like that one. How does it work? How do you figure it out? So here's different types of movies, the little pictures on there, scary movie, horror movie, drama, comedy, whatever. So there's and this is why sometimes people say unstructured data is important when you think about AI, because these movie descriptions are unstructured data. They're just paragraphs about the movie, right? And what you need to do in machine learning, and this is zeros and ones again, it's like you break it down to the basics. So that vector on the bottom, that's what they call it, right? All it is a sequence of zeros and ones. They try to make it fancy and call it a vector. But what you do is you need to figure out of the way people describe movies, how many key words are in there that you think should be vectorized in the mathematical description of the movie. And so what machine learning does is it does this on its own. You don't have to figure it out. Is you start to feed it all these movies with these descriptions and tell them which ones you like, which one you didn't. The machine learning algorithm will actually go through all the descriptions of the movies and figure out on its own key words, key phrases, key sentences, key paragraphs that say, okay, I understand now why he liked this one, why he didn't like this other one. And it starts to form the algorithm, okay? So that sequence of zeros and ones are important because, like I said earlier on the explicit programming, I was never sure how many differentials to keep in an equation. Like if you look back at my education, I'm an engineer and a mathematician. It used to horrify me because I'd be in my math classes and I was an applied mathematician, so we'd be looking at how you design bridges and that kind of stuff too. And I'd have an equation that had like 10 terms in it, and we figured it out. I'd go to my engineering class and it would be the same problem, but the equation would only have 3 terms in the engineering book. And I went to the professor, I said, where's all the rest of the terms? He says, we're not sure if those are going to apply or not, so we just call it a factor of safety, multiplied by 5 or 10 or something. Oh, all right. So it's which terms are important, right? So that's why explicit programming is hard. But machine learning, you also need to make that decision too. You are what you eat, right? So we need to let the machine learning, and this is what's called training the system, you need to make sure it picks up on the stuff that's important, right? So what's really important in these descriptions, if it misses something, then you just tell it, and it adds that in as part of its learning. So what ends up happening is it goes through and it creates these vectors and it assigns zeros and ones. These zeros and ones are labels. So that's what's called a label. So your bottom part thing is what's called a vector if you read about it. And then these other ones are called labels. You like it, you don't like it. 0 plus 1 minus 1. So then you've got these equations, x of 1, x2, x3, x4. And so now you've got the graph, right? So the question is, okay, you got a couple of minuses on the left and you got a couple of pluses on the right. And now you've got the new movie, all right? How well of a predictor is it? So now we drop the new movie in with its description. The machine learning algorithm is going to look at it and say, well, do I recommend it or do I not recommend it? So basically, you've got this graph, and these are the initial examples we came up with. 2 you liked, 2 you didn't like. Now, what happens a lot in what we do today, and this is why that explicit programming is a problem, we always try to linearize an algorithmic approach to solving a problem. Whether it's linear all on its own, you can do things, if a function is naturally exponential, you can transform it so it looks linear when you're doing your analysis, your prediction. Same thing with log functions. You can linearize those as well. So our big goal in life is always to try to linearize and do regression. In this case, that would have been a disaster, right? Because if this is the line, and then I have a new movie coming in, well, the line doesn't really represent my choices because half is plus, half is minus. What I need is something like this. So that the machine learning algorithm says, yeah, I know the difference between what you like and what you don't like. So the machine learning algorithm would actually create this line as opposed to this line. And that's why it's so hard to tune explicit programming and continuous mathematics, because this is typically your starting point, whereas machine learning is going to put you right in the zone of what you're trying to find out. So now you've got this machine learning function. It knows what you like, what you don't like. So what you do is say, okay, let's take some new movies and put it in and see if it works. And so that test set comes in, and then it proves it out, and it learns and keeps learning. So this is how the Netflix recommender works, at the high level. They create those vectors based on the features of the movies, and then you get those recommendations. Natural language is about the same. There's just more vectors, that's all. Because a paragraph has words, sentences, a segment has words, sentences, and paragraphs, right? So now you need 3 levels of vectors. And this is why natural language programming has exploded in the last few years. Chomsky was the one that initially defined and designed it years and years ago, but he always felt that neural networks wouldn't work for programming, so it was all brute force. The French dictionary, the English dictionary, blah, 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 and you try to brute force how all the translations work, and it really, for those of you that tried to use it over the years, it was so-so. You know, a lot of times it was wrong. The improvements they've made now by vectorizing it, the same way that we're doing with the movies and descriptions, the accuracy is going right through the roof. So this is why you're going to be able to use NLP, whether we're in the warehouses, whether we're doing ordering, whether we're doing inventorying, whether we're using an Alexa skill like I showed earlier. This is why this is being revolutionized right now. Okay? It's going to be for written, and it's going to be for speech. The image technology is a slightly different thing. All these other ones I've been talking about, I mean, you can be more right or less right, but you're still right. So yeah, that movie, yeah, they recommended it. Yeah, I really liked it. Yeah, it was okay. You know, watch it. So you're never quite wrong, right? There's always these zones. The problem when you're taking pictures of your products at retail is that people want you to be 100% right. I said, well, either the products are there or they're not. Can you take a picture, and can the picture interpret what's on the shelf? Can I figure out my market share? Can I figure out what's happening with my promotional success? Can I figure out any voids that I have, any stockouts, any issues, that kind of thing? And so this one is very similar, I guess, to the evolution of your phone. Right now, there's a couple of digital image recognition vendors out there. People have been trying a lot of things with them. But the range is about 80 to 98%. The soda bottle, stuff like that, the simple stuff, you're getting about 98%. The more complex items, yogurt with tiny little variants here and there, sprinkle this color, sprinkle that color, whatever, that's harder. The other problem is the environment that the pictures are taken in. There's a lot of different lighting conditions, there's a lot of different settings, there's a lot of different backdrops depending on where the products are. Main shelf, top, bottom, end cap, wing display, whatever. It's hard to teach these systems. There's a lot of expense right now in the Gen 1 and Gen 2 systems. That's why you're being forced to pay 10, 12, 14, 15 cents a picture. And it's harder to get a return to your field sales rep while they're still in the store if you wanted to take action based on the picture. So this is still in its infancy, this technology. Gen 2 is kind of like the flip phones. That's where the current DAR vendors are today. The Gen 3 are going to be more like when the iPhone 3 came out. And those are currently under POCs. So there's some proof of concepts. These are more the smaller companies, the startups. They could be pretty much in any country. But it's really that Gen 3 that's going to have an impact here. So if you're thinking about this stuff, it's going to get better. I know it's been a struggle so far. We don't develop a lot of this on our own, but because the vendors that we're available to work with and partner with have been struggling, we did start doing some of our own work in this area. Yoon, who runs China for us, is here. He's the one that's been doing a lot of this cognitive computing for the picture taking. The way we're doing it, it's quite a bit cheaper per picture, but it's more as part of the audit business that we do for a lot of the big consumer companies across Asia. So, but if you want to talk about it and hear about what he's doing, Yoon's here as well. Yoon, is Yoon in the room? Yeah, there he is right there. So, yeah. So that's what's happening there. So why now? There's a large amount of available data. The computational resources that I talked about. So you got your big data, you got your computational resources. It's pretty straightforward to train the algorithm, as you just saw in the Netflix example. And the other thing is, and especially on natural language programming, is what we discovered as we went into deep learning with the neural nets is that you can actually create plug-in components almost like Legos. So that's why it's getting so good in terms of language translation, text translation, and so forth. So a lot has changed over the last few years, and it's all come together now. Now, we're all a community here. So there's also some dirty little secrets about it, you know, what's under the covers here. The data's never clean. Like I said, for the last 30 years, it's about storage and retrieval with our data, not interpretation. So now we've got this new challenge. We need to make the data interpretable if we want to play in this game. It's our data. If we have a pile of gold sitting there, why not mine it, right? So we need to think about schema changes around the data, so that we can make it more useful, and we have to make sure the data is clean. In a lot of cases, linear regression is still adequate. Linear regression is a form of AI in our general AI duffel bag here. So we can continue to use linear, and as a matter of fact, you can run linear parallel with some of your machine learning algorithms, just so you compare predictive outputs. That way you have one compared to the other, more traditional, more new, and just see how things are running. You already have the data. So linear regression is still going to be useful. All models have error, but some are useful. As I said, the explicit programming, continuous math approach that I used to use had error, and I wasn't ever sure where it was. At least here, I can typically figure out where the error is because I'm just looking at what the predictive outputs are. Some are useful, obviously, because like I said, you wouldn't have seen 3 AI commercials last night on the hockey game if it wasn't useful. Companies are getting benefit out of this. Bayesian will be in play. Now, this is for those of you that might be more in the data science field. I'll just mention it briefly. A simple example of Bayesian, let's say you plan on flipping a coin 100 times, and you flip it 40 times, 25 are heads, 15 are tails. Okay? What does that mean? Does that mean you have a biased coin that's more heads, or when you finish the 100, do you think you'll be closer to 50-50? What's the data really telling you? This is the difference between probability and statistics. Because if you have the coin's 50-50, it's a fair coin. But you could have 25 heads, 15 tails in your first 40, and then you might end up with 50-50 by the time you get to 100. So, but probability tells you that's not going to happen. It's going to say, even though you had 15-25, going forward, it's still 50-50. Right? So the other 60 is going to be 30-30. That's probability. But statistics is telling you, oh, wait a minute. Over 100, I think it's going to even out. That's what Bayesian means. So as you look at data, especially because machine learning is so dependent on data, some of these influences about whether your data is biased or whether it isn't biased is going to come into play. So as you start to engage over the next few years and you start to think about machine learning in your businesses, that word bias is going to be something people do talk about related to your data to see if it's present in your data. And that's what this is. So it's just going to be something that we'll have to consider and deal with. There's no fully automated solutions, really. For any machine learning, I like to have a human involved in the process, can look, evaluate the outputs. What you may want to do is put like bands together. So once you get comfortable with the machine learning algorithm, if it's going to give you a predictive rate to say, yeah, I can say that if you do A, you're going to do B 90% of the time, you may say, okay, that's good enough, let's automate that, or 95% of the time. If it says, if you do A, you're going to do B, and my confidence is 80 to 95%, you may say, okay, I may still do that, but I want someone to look at it. And so you push that out to a person, and they'll take a look at it and make a decision what action to take. And you might say, if it's less than 70%, we're never going to do it. So let's tell the system that, just to discard that one. Right? So you can put together different zones about how you want to handle it. And I also mentioned the data lakes, refineries, repositories, and stuff are just tools. So don't let somebody sell you on some big multi-million-dollar project to create this stuff, because that's not what's going to get you the results you're looking for. Over time, you might create these, but they're just tools like anything else. The programming progression, it's not unfamiliar to us, right? This machine learning isn't some big, dark mystery. Lisp, Ada that I talked about earlier, C, MATLAB is still in play for those of you that ever used that. Python, the random forest that we're using in an example I'll show you in a second here from our TPM group, it was used to write the random forest algorithm. Now, Python is not about a big snake going to eat everything. Those Monty Python fans in the room, anyone remember Monty Python? That's what this is named after. R was named after a couple of the founders. Their names began with R, so they called it R. That plays in there with a lot of stochastic statistical analysis. And then, of course, we have our Java and JavaScript and C#. So the languages are all familiar. Now, what we've done with the languages, though, is created all these different ML algorithms. So you've got the random forest that I talked about. You've got gradient boosted. There's a whole bunch of them. They're all good for different things. So I put that in on the right-hand side. There's a lot of duplication in there. Some of them can do the same things, but they're good for different things. And so what you want to do is, based on your data well, and as I said earlier, you are what you eat. So you need to look at the data. You need to look at the features you have, whether they're structured or unstructured, and then decide which of these algorithms. You can use multiple of them. I'll show you how we did it through the Excedra group, looking at all the different algorithms just to see, well, which one is going to deliver a more consistent, better predictive result. If A happens, then B happens, and be able to test that. So there's a lot of different ones out there that you'll see. As I said, it relies on the data. Not only do you have your own data, there's a lot of data out there, right, that we have access to. We got retail data, we get sales data, we get CRM, the social media data people talk about a lot. I don't know if any of you saw the Brexit movie about how they manipulated the social media data in order to get the vote. Pretty interesting on how they found the undocumented voters, about 3 million of them. What they would do was put out bait ads to track behavior, and then who responded to the bait ads are the ones they would target for voting and things like that. It's very interesting. Loyalty card data is out there. We got consumer financial data, voting, on and on and on. So there's no lack of data. We just have to figure out how it plays into the machine learning and the kind of results we're trying to put together. DARPA will continue to influence. As I mentioned, my father-in-law Frank was funded by DARPA when he invented the ARPANET with his team. They're still in play. There are national security issues around this. Now, the Gen 3 image recognition stuff I'm looking at, we're looking to partner with companies in China. So this is a global market. We all operate globally. But there's also investment coming in from the US government because they don't want other countries to get ahead of the United States. So there's all kinds of funding that's coming in trying to take AI to the next level, giving machines common sense, helping them learn faster. Learn faster is going to be really important to us. The faster we can get the systems to learn off the data, of course, the faster we'll be able to put out better predictive results in running our businesses. Decision making, I mentioned earlier, grabbing the coffee, it's hard. So they're going to try. They're going to try to give systems like an overlay that can at least explain at some level how the ML algorithm came up with the answer it did. Okay? So a lot of governmental investment coming in from DARPA. So the uplift method, this is a quick example. So trade promotion uplift, basically gathering a year's worth of history, customers, SKUs, the length, discounts, and so forth. Calculate the uplifts. We're going to test multiple models. I'll show you those in a second. And then determine the attribute importance. So first, here's 5 of them. So there's gradient boosted, random forest, something called support vector machines, all kind of weird names in these things, k-nearest neighbors, and then linear regression. So which one has the smallest mean absolute error? In this case, gradient boosted had the smallest mean absolute error. So this is the one for this particular data set that would probably be the right machine learning algorithm to use to get the best reliable predictions. If I did A, then B is going to happen, based on the data and the test that we gave it. And then the other thing you want to do is you want to try to whittle down variables that aren't as important. And so you start to do mapping on importance, because the machine learning, in this case, you can see all the different variables it used to create its algorithm. And you don't want to have to deal with that much data if you don't need to. So what you do is you say, well, what are the high runners? And so then you whittle down that matrix. Remember those zeros and ones? Now you can whittle it down to 6 and say, let me see if the predictions stay just as good just using the 6. And then you can whittle it down, and that it makes it a lot easier. You can teach it more data, make it learn faster, that kind of thing. So we did that. And then the other thing you want to check on is the residuals are the errors. So in this case, for trade promotion management, trade promotion optimization, you've got a very small distribution of residuals, which means there's a very small error, just a little bit on each side. Any of you that are using a TPO system right now that's based on what I said earlier, explicit programming, continuous mathematics, the old optimization stuff, you are going to fall behind if you continue to use that kind of stuff. You need to get onto these machine learning algorithms in TPM if you really want to have a good TPO view as to what's going to happen in the future. And if you stick with the algorithm approach, like I said, it's okay for now, it's the best we had to work with, but you're not going to have a system in play that's learning, and you're going to quickly fall behind over time. So the uplift method in play, I'm going to randomly select, and so this is how it learns. So this is just a continuation of that. So that's available today. The Exedra folks already designed this, and it's already been rolled out to some of the customers. The next one, just looking at retail itself, there's a lot of different AI machine learning based capabilities that we're enabling our apps with today. Shelf trend predictors. There's visit plan automation. We've got visit execution in terms of the tasks and surveys and actions that you want the folks to take within the visit itself. Some of this involves the coordination of the digital image recognition I talked about before. That's why we're focused on figuring out how we're going to partner there. We've got the omni-channel collaboration. There's a lot of different channels that are involved: back office, front office, field sales, merchandising, distribution, delivery, inventory, making sure that we have a dashboard, an executive dashboard that runs across all that. Now, some of these rely on general AI stuff. Some of them rely on narrow AI, like I showed you with the Exedra, and then some of the stuff we're doing on retail execution, and some of the things we're doing in supply chain. So it's a mixed bag right now, and you want to have a little bit of both, because I said the general AI is what got us to where we are today. So regression is still in play, and it's still going to be important for us, but you need to start mixing in some of the narrow AI too, because that will continue to learn and get better over time. So these solutions I'm showing you are a mix of both. And also, of course, perfect store. So there's also a little POC here.
This is a demo of the new AFS order management system that makes life easier for you and your customers. With OMSI, your customers and IoT can simply use a smart device, a phone, a watch, or Amazon Echo to order items from you with their voice. Just say, "Alexa, open AFS." Place an order for the quantity of a specific item, like milk, orange juice, bread, or anything that you would usually order. With simple voice commands, build an order list, say "Done" when complete. Alexa will confirm and give you an order number. At your food distribution center, you will have full visibility into real-time incoming orders that you will fill and reconcile with AFS OMSI. Happy customers and simplified ordering. AFS, systems that make your life easier.
So that's a proof of concept, and that's a task. So natural language processing has gotten so good now, and you get the Echoes and Alexa processing systems and so forth, you can program tasks in to do a lot of those things now. So if you're using VoCollect in the warehouse, you're seeing it live today, for those of you that are using WMS, with voice translation and controls. and it's going to only expand from here. Okay. So the value and benefit, and if you look at what the analysts have published, for companies that have started to apply ML, these are the kind of results they're getting at the process level, KPIs, stockouts, things like that. So they're getting some pretty impressive improvements based on replacing the old algorithms. Like I said, we did our best, but we had what we had. Replacing those with the machine learning algorithms, the results are certainly improving. So what I've done is, now, I'm not a fancy marketing guy, so I went to Walmart, and to create our narrow AI bag, I bought these styrofoam discs. So I'm a whole hockey player, so I use hockey tape. But so these are the different groupings I have of our AI-enabled applications, okay? Some of them are available now, some of them we're developing, and some of them are a mix of the general AI plus the narrow AI, okay? And as I started, we're a community, and we're gonna work together, and we're gonna figure out what these new technologies mean, how they can create business value, how to make them better. And so that's why I'm exposing you to all this. Some of you, it may be years and years and years before you ever look at any of this stuff. Some of you are looking at it today. But as we work through it, we can figure out what we want to do. So what I've done is I grouped them into different strategic, tactical, and execution level type AI capabilities. So the strategic group, I grouped our promotion lift prediction, which I just showed you, sales opportunity creation, 360 revenue insights, which is that collaboration, and then the revenue intelligence. So there's different capabilities we can provide that will provide insights to the business that more kind of back office, how you're going to plan the business, and what do you want to think about, what do you want to do. So that one gets to go into our narrow AI bag, because we're going to continue to evolve that through machine learning and deep learning, if I can get it in there. All right. And our next one, I could have just used the paper, but it wouldn't have filled the bag. So. The tactical piece, so revenue performance. And some of these names, I have to confess, I saw them, some of our competitors out there calling this stuff that, and it was nowhere near as good as what we had. So I thought the names were good. So some of the names are the same that you'll see with some of the competitors. Revenue performance, shelf trend prediction, and Michael's actually modeled a lot of these in G2 already, the approach that we're going to take. So for those of you that are familiar with G2, it's a pretty graphical view, representation, understanding of what we're going to do here. So we do have some of this stuff that he'll be able to show you. In addition, of course, to what I showed you from Exceeder, which is a working machine learning algorithm. The shelf trend predictions, suggested orders, predictive orders, these are big things. The suggested and predictive orders are really important right now. A lot of people are looking for solutions there. We're heavy and deep into this now on machine learning. And of course, the churn reduction. So these are a little bit more tactical. And then on the execution, I ran out of discs, so this one's a double-sider. So let's see, this one here, let's see. Oh, wait a minute, I'm gonna go to the next one. All right, visit plan creation. So this is really when you're in the field and you're working, you can still use AI to give you some insights as to what to do next, what to do best, what decisions to make based on the data that's happened before. As a matter of fact, on the execution side, maybe it's even more important, right? Because at least there, the machine learning is saying, hey, I know what happened last Tuesday, or the Tuesday of the month before, or when one of your competitors made a promotion the same week you're trying to make one. I know all that stuff. So I can give you some suggestions on what to do about it, depending on what your KPIs and your targets are. So we've got the plan creation, the execution, omni-channel, and perfect store. And then on the other side, I've got, and this actually is more in our food service area. So food service, it could apply for anyone who's managing contracts. But as all of you know, in food service, a lot of the relationship is governed by how the contract execution works. And so there's a lot of rule-based already. Now, rule-based is general AI. We haven't actually applied the machine learning there yet. But there's a lot of rule-based that's already embedded with targets and guardrails and things like that, KPIs. Around contract automation, the settlement automation, we already do deduction auto-match, and spend exposure liability. So these things are already in sort of the general AI category. And that's what I mentioned earlier is there's a lot of vendors running around saying they have AI and blah, blah, blah. What they may try to fool you where they try to show you an ML type algorithm but it's really just for demo purposes. It's a limited data set. They're going to show that to you, and if they actually do anything real for you, they're going to go back and use the old stuff and generate the answers that way. So there's a lot of that that's going on in the market right now, so keep an eye out for that. So this stuff there is pretty good. Put that in our execution bag here, in our arrow. And then finally, I mentioned on the voice, we're already doing voice-enabled in the warehouse right now, voice picking, those types of things. We work with our partner, Vocalect, on that. But we also have some work that Gennadi's been doing, and some of these capabilities will be coming out in the next 6 to 12 months. You just saw our little proof of concept there with Alexa. Voice-enabled ordering, the delivery assistant, and the predictive inventory purchasing. That one's a little further up, but that one's going to be really cool. Over the years, I was involved in the early days when we first designed ERP and then supply chain. I actually have the patents on supply chain from I2 on multi-enterprise supply chain. And this one on predictive inventory purchasing could be real interesting because obviously inventory carries a lot of weight when you're looking at value props. And if I can start to develop a machine learning algorithm looking at patterns over time through the ERP system where I can do predictive inventory purchasing, that's obviously going to have a decent return on investment. So that's one of the key things on that whole ERP supply chain side that we're looking at. Okay? So, yep. So the key concept for today, and I know I threw a lot of stuff at you, but I just wanted you to at least get a foundation because you're going to get this stuff thrown at you. It's going to be on TV commercials. You're going to have vendors running around telling you this, that, the other thing. If you're a big company, the analysts are probably going to be asking your executives during the quarterly calls, what are you doing about AI? They're going to run around and ask everyone, what are we doing about AI? I could have an answer. So it's going to be an important thing to talk about. But the one key concept, just to keep in mind, is to keep it simple. Remember, zeros and ones, all this stuff, is it's a form of AI that enables a system to learn from data rather than through explicit programming. And that's really it. That's the crux of the thing, is that now we as humans, we learn from storytelling. And we haven't been able to do that with computers until now. Now what we can do is take the stories, the data that's been produced about what we're doing, that's the story, and now we can use the story to teach the algorithm to make better predictions for us in running the business, rather than all the stuff I used to do where I was trying to fine-tune these maddening differential equations to get better results from predictions. So again, the other thing I mentioned, remember, with the linear programs, I was able to show someone, hey, well, how'd you get that? Well, here you go. Take a look at it. It's 3 pages of equations. With machine learning, we're not going to be able to do that. Right? You're not going to be able to say, well, here's exactly how it came up with it, because it's a learning and neural net system. So that's the one big difference. So hopefully this was informative for everybody and gives you a foundation to think about this stuff. And we're working on your behalf and moving us forward. Again, our core development, like I said earlier, is what you're telling us. This is just a little branch that I'm doing. So all the money you're putting in, I mean, you'll see it today from your product manager. It's all your competitive advantage, the tech debt, the maintenance, the catch-up stuff. That's where the development's going. This doesn't take a lot of expense. I mean, on the Excedra side, we've only got, I think, 2 folks, Richard, doing this piece on the machine. Yeah, so it's really, it's not a heavy burden on expense. You just need to know what you're doing. The most important thing is to have industry knowledge, because as I said, these data wells are particular to a particular problem. If you don't understand the problem, then you're not going to be able to tune the machine learning algorithm well enough to give you good predictive results. So it's all about how deep you are in the industry. This isn't something where all of a sudden I'm saying, hey, Joe's going to divert half our development dollars into this thing that I'm not even sure if it worked. I only need a couple of people to do this. So this is a little bit different. Okay? All right. Well, thank you, everybody. Appreciate it.
Turn your magic on. With me, she'd say everything you want to dream away. We are legends every day. That's what she told me.